His, after getting his PhD from the University of Beirut in theoretical physics, he moved to UCSB as a postdoc in 1991 and soon after as assistant professor of physics to Cornell, where he rose through the ranks. After about a dozen or so successful years at Cornell, um, Eberhard was chosen as the director of the Max Planck Institute for Dynamics and Self-Organization in Göttingen, which he created and he still leads. You will no doubt remember that Göttingen was a celebrated place in physics and mathematics before the Second World War. It was an especially illustrious place for fluid dynamics and turbulence, and Eberhard's appointment there definitely brought some of the luster back to Göttingen. Among other things, Eberhard has built two unique experimental facilities there, a variable density wind tunnel and a high Rayleigh number convection experiment. I'm sure his talk will cover the first one. He's also a professor of physics at the University of Göttingen and has taken on various leadership roles at the Max Planck Institute, Max Planck Society, which is the parent organization for all Max Planck institutes. In that sense, he has become my boss as well after I was elected the scientific member of the Max Planck Society. Eberhard is a fellow of APS and is a recipient of the 2014 Stanley Carson Award. For all these wonderful reasons, I am very pleased to invite Eberhard to give us his colloquium on whether or not turbulence is universal and welcome him on your behalf. If there are questions, Alexandra, maybe it is better that the audience write them down in Q&A. Towards the end, you or I will read them out and Eberhard will answer them.
Sure.
Is that okay? Yeah,
That's fine.
Eberhard, the floor is yours. So
Well,
in an unconventional way, we welcome you. Otherwise, we would have done this, all of us. But now I do it on everybody's behalf.
thank you. Thank you very much, Srini. Thank you for having me. It's really nice to be here. It would have been nicer to be in New York and wander down the streets, but I guess not possible these days. So I'm going to talk about fully developed turbulence. Is it universal or not? This is mostly new stuff that we have been doing over the past years. And just to show you that our institute is universal, is international. Here's a picture of our institute where we had these flags up. Now there are less of them. We removed half of them because it was just a little bit too much, but they're still there. And so it's a very international institute. We have about in the institute we have about 300 people. About 160 of them are employees, so 180. And so it's quite a large institute with 3 directors, and it was formerly, as Srini said, it was the Flow Research Institute that Prandtl founded in 1925, and now it's called Max Planck Institute for Dynamics and Self-Organization. So I wanted to talk about, let's see whether it actually works. Yeah, here we are. And so most of you actually know what turbulence is, so I don't have to say much, but it's since Srini is there, I'm sure he has given more than one talk on this topic. But you know what's important is this Reynolds number, and the Reynolds number is basically nothing as a dimensionless measure of the inertial forces over the viscous effects. And here I have a few numbers. So the typical Reynolds number for a coffee cup, where you see the turbulence very nicely, is 10 to the 2. Then for a fire might be 10 to the 3, and for a volcanic eruption it might be 10 to the 8. So the Reynolds number can be very, very high. What you also see here that I don't have a picture of turbulence. There's always a picture of turbulence with something in it, because turbulence you can't see. Turbulence is just, it's just the flow of the fluid. And of course, the fluid to make it visible, you have to put some tracers in. And so in these pictures, you can see these tracers very, very nicely. And I asked the question, can it be universal? And, I'm ready. So this is turbulence when you make it visible to the public. So what I do is I give public talks on cloud physics and turbulence. And so here you see me on the left side standing in a room in a lecture hall, and you take just a nebulizer, you make a fog. Actually, this one was made by Alan Premier. And then there's a German guy talking in the background.
Alain, can you explain it?
You see, I just asked Alain to explain it. And so what you do is you make this fog, and then you see the inhomogeneous mixing of the turbulence. So you see basically the turbulence structures very, very nicely. It's weak turbulence. It's just right in the room to be at the time scale of a human being. So it's lucky. It's a lucky coincidence that you can do this. It's like art. I highly recommend it for you to play this to do this in a lecture hall. It's really, I can show you it again. It's because I'm do this a lot, but you can see these amazingly structures. You can see the fine scales. You see how a passive scalar is being mixed in turbulence. Diffusion doesn't play a role here much yet, because all these droplets that are in the air basically are being mixed. And it's really fascinating to watch. And there's an artist in Switzerland who made already a exhibit out of this, where he plays music to entrance you into these structures. So it's quite amazing. And so what is this turbulence? Well, the scales in turbulence are such that there are these really large scales. Here I pretend the large scales are given by this L. That's where energy is injected in the flow. And then on this picture, you see many, many smaller scales at once, right? You not only see this large scale, but you see also the smaller scales, and they all seem to be on this picture. And this is very important, because a big part of the understanding of turbulence comes from pictures like this. So one does not actually look at the temporal evolution of this structure, but one looks at pretty much at the spatial evolution, or the spatial structure. You can see on this figure, you can see large vortices. And then if I would take away this thing here, you would see within that, you see smaller vortices and smaller vortices and smaller vortices, all the way down to the viscous scales of the fluid where energy gets dissipated. And for that, so there's a so-called energy cascade. And this is why we believe there's some universal property to turbulence, that you have basically an energy injected at the large scale. Of course, it makes only sense to talk about the energy per unit time. So this means power. And of course, per unit mass, because since inertial effects are very important, unit mass plays a big role. And so epsilon is basically the energy you put in per unit mass at the large scale. So power per unit mass. And at the large scale, things, of course, not universal, because it depends how you make the turbulence. If you make it with a fan, you get a different turbulence at the large scale as if you make it with Mother Nature, with the wind driving over the surface, and so on and so on. But the question is there something universal to that turbulence? And we know for a long time, since Kolmogorov and Taylor and Prandtl, that there is in Heisenberg and Weizsäcker, we know that there's an energy cascade. And so energy goes from large scales to small scales. And so we can understand this one picture that I showed you just by saying that there's large scales, there's small scales, and between these scales, energy is being transferred, and this energy will go down to viscosity. For example, there's right now a discussion whether an air cleaner in a room is a bad thing in a classroom because it uses so much energy. I answer no, it's not a bad thing for a classroom, because all it does is produces heat, and it heats the room. So it's a good use of energy, because it also keeps the COVID-19 virus away from you. So because it's also heating the room, right? It's better than opening the window, which of course has other reasons, because you want to get the CO2 out of your thing. But a filter is actually not bad, because all it produces is heat. And so it's a good way to heat right now is to have a filter in your office or in your room, because it gets rid of the stupid virus. And so what you have is you have the kinetic energy, of course, in the flow, which is given by the mean velocity. You have this energy injection scale, which is this large scale that I have put in. And then at the small scales, you have the viscosity that dissipates it. But what's important, again, is the kinematic viscosity, which is the viscosity divided by the density of the fluid. And if you look at this, you can look at this in many ways. One way is just to make a dimensional analysis. Another way is actually to look at a self-similar process, which might be Gaussian. And then at the end of the day, if you look at everything, you've realized that there's a small scale, which you can make up, where the local Reynolds number is of the order of 1, where dissipation should take over. And that scale, as Prandtl put it, for the lack of a better idea, there must be one length scale and not a variety of length scales. And so for the lack of this better idea, we have this. Nowadays, we know there's probably multiple length scales involved, but the Kolmogorov length scale gives you a good idea of the smallest scale in this flow that you have to resolve. To give you an example, in a turbulent cloud, which is the most turbulent thing we have on Earth, you have a large scale of about 100 meters and a dissipation scale of about half a millimeter. So these are all the scales where the turbulence might be universal in nature. It's interesting also to note that the largest turbulence levels on Earth would be then like a volcanic eruption or large-scale turbulent flows. Actually, the Reynolds number is limited. You cannot go up to a much larger Reynolds number on Earth. You can do this on stars and planets, other planets, but not on the Earth. You're limited in things. And so Srini is now working on the sun, and he can do, of course, a little better than what we can do on Earth. But it's always limited. It's not like its infinite Reynolds number is really a realization on Earth. We can try to do this. And so the Reynolds number tells you the inertial over viscous forces, And of course, you can see here in this definition that I have, it depends on the scale. So you have scale, a velocity, a scale, length scale, and then you can define a local Reynolds number, and it's 1 if you are down at the Kolmogorov scale. And so one problem with this definition is that this definition of Reynolds number depends arbitrarily on some length scale, which might be a correlation function or something. It's easier to actually measure the correlation function and to follow G.I. Taylor, who invented a different Reynolds number, which is based on the so-called Taylor microscale. And so the length scale has been replaced with a new length scale, which comes from the initial decay of the correlation function, which is easy to measure because it's only the initial decay. And from that, I get a nice length scale, and that length scale I can measure for every turbulent flow I have. And from this, I can basically now get a Reynolds number, which I can carry over from experiment to experiment to experiment. I don't have to worry too much about what the real energy injection length scale is that you put into the flow, although it can also be measured. And so for this, I wanted to introduce you to the facility, and for this, I let somebody else talk, namely this guy.
We are here at the Max Planck Institute for Dynamics and Self-Organization in Göttingen, Germany. We are part of the EU HIT network. Here we have 3 large facilities. One is the wind tunnel, which is behind me. Then we have the Göttingen U-boat, which is a high pressurized convection facility. And then we have 2 experiments that allow us to do Lagrangian particle tracking. One is the crystal ball and the LEM, the Lagrangian exploration module. Our wind tunnel is very special in the sense that it can be pressurized to 15 bars with a gas. The gas that we're using is sulfur hexafluoride. Sulfur hexafluoride is a very heavy molecule. It's at atmospheric pressures is 6 times heavier than air. So in a typical experiment with an active grid, we get about a turbulence level that is comparable to the atmosphere. At the same time, the scales go for roughly half a meter all the way down to 10 micrometers. The U-boat is about 6 meters long. It is about 5 meters high. It looks like a U-boat because it has a turret. And in the air, what we can do is we can place convection experiments, like, for example, this rotating convection experiment. We then take a turret and close the whole system, and then we can pressurize it up to these 15 bars. By this, again, we get very high Rayleigh numbers. In that case, what matters is the temperature difference, and again, of course, the kinematic viscosity. So we have very strong turbulence level. In the seed transport experiment, we produce one of the highest Rayleigh numbers in a laboratory that have been achieved so far. A third experiment, which is currently not in the U-boat and not in the wind tunnel, are our Lagrangian exploration modules. One is using water, which we call the LEM, and the other one we call the crystal ball. It's a sphere made of plexiglass and looks like a crystal ball. In both of those experiments, we can study the Lagrangian dynamics of particles. So we can look at particles in the, for example, in the wind experiment. One could also imagine to put in some flies and see how flies react to a turbulent flow. Or one can ask how is our rain droplets formed, how are the collision probabilities for heavy particles, what is the settling velocity. There's a whole range of many interesting experiments one could do. So there's a lot of opportunities here to investigate very carefully natural phenomena, but at the same time, very fundamental phenomena about turbulence.
Good.
We are here at the Max.
So I don't want to play it a second time. So this gave you now a nice introduction to what it is. You can download this video from my website. It's online. This was a structure we had put together with the European community, which the grant since then has expired, which is a pity. But here you can see this wind tunnel. So the wind tunnel is about 18 meters long. And what we have is we have only 200 kilowatts of power, which is very little for a wind tunnel. It's almost nothing. It's like if you go down the German Autobahn with a Porsche, you produce more energy, you use more energy than my wind tunnel. So it's a cheap experiment to operate. It's much cheaper than to simulate turbulence. It's also much more energetically efficient than simulating turbulence because these big computers use much more energy than my wind tunnel will ever use. And it's 1.50 meters in diameter. And of course, we have to make sure the flow is well behaved and so on and so on. And so here's a picture of this wind tunnel. So here we look inside. And so in the back, you see, so this is the measurement section. It looks a little funny. The reason is that underneath here, we want to do particle tracking and want to drive with the wind. And so that's why it's a little bit oblique. There's a rail that actually allows us to drive with the wind sometime down the road. And here's this active grid I talked about. And so what you do is when you generate turbulence, you blow turbulence usually through a fence, a grid. And then at that grid, you get vortices, you get a convective instability, and then these vortices get shed off, and then these vortices interact with each other and produce turbulence. And then you get something like I had shown into this room. And so you have to go far away from this grid, otherwise you can't get homogeneous situations or isotropic situations, statistically homogeneous and isotropic. And so here is a picture of the grid. So here's the video. So here you see this grid. And so usually what people do is they have a stationary grid. And then when Greg Bewley was in Göttingen, now he's a professor at Cornell, we decided we build an active grid where we can move each individual flap. So here we have 111 flaps. You can imagine these are valves. And we can turn these valves. We just basically, this is a flap, it rotates by 180 degrees. And with this, we can actually drive the turbulence, and we can introduce different correlations in the flow that in a normal grid you cannot have. So if you have a stationary grid like you would have here, like this grid, you would not be able to do that. And by this active grid, we can write in certain correlation functions and so on, and can basically produce a turbulence which is very well behaved and very high turbulence levels. The additional advantage is that since your tunnel, of course, has boundaries, you can make the flow profile flat by just changing the angle that you open up these flaps. And so by doing this, you can also make a very, very homogeneous isotropic flow, or you can make a shear if you want. So you can, I could have now written some letters, I could use some alphabet, I could do whatever I want. But one thing we do is you write in a random flow and make a correlation function. And so what we have is we have a correlation function in space across the wind tunnel. So we have a certain spatial correlation length. And of course, in the time domain along the wind tunnel, you have the time domain because you're opening up these flaps. So what that means is you get, out of this one, you get a length scale squared, which is the transverse. And longitudinal, in the direction of the wind, we get multiplied with the mean velocity, you get another length scale. And so you see that this gives you some kind of correlation volume. And then what you can do is out of this correlation volume, you can calculate a correlation length just by taking the third root. And then if you plot the measured correlation function as a function of this correlation length that is this given out of this V core, then you see there's a relatively nice relationship going up to 1.50 meters. That's basically the width of the wind tunnel, by the way. And so when we do this analysis, we can also define a grid Reynolds number, which is just given by this correlation length, which I've just shown you, by the mean velocity, the sine of the angle of the opening angle. So it's at 90 degrees, it's fully open, it's 1. And then here, this is the kinematic viscosity. So if you take that one and you measure this Taylor microscale Reynolds number in an experiment, what you find, you get a very nice straight line. Please ignore this point on a newer slide. This is not there yet, but not there anymore. This is not sensible what this point comes from, but just ignore it. And so what we then can ask ourselves with this wind tunnel, which is now it says only 200 kilowatts. We have to take, of course, the heat out of the tunnel with every turn. We have to reduce the temperature by 0.1 degrees, roughly, when you put 200 kilowatts in 8 tons of sulfur hexafluoride. So the wind tunnel would be pressurized to 15 bars. It would be filled with 8 tons of sulfur hexafluoride. And the sulfur hexafluoride at that condition has the advantage, it has a very, very high density, but a very low viscosity. So that means that the kinematic viscosity is very, very low, which means the Reynolds number is very high. And so here you see a plot. So this is the Göttingen wind tunnel here. And these open ones, these ones are the VTTT, which is down here. And then there's other experiments where people have done. There's also atmospheric boundary layers that Srini has pioneered. And so what you see here is that there's this very nice scaling range. And we're really adding currently to the experiments. This is the Honorar wind tunnel, which was originally a German wind tunnel, which goes up to here. That wind tunnel costs in operation for 1 week 500,000 euros. So this one point costs probably of the order of 500,000 euros. Okay, so what that means is it's very expensive to run this. I can run my wind tunnel forever, doesn't cost much, and so I call it a tabletop experiment, although it might not be. And so what you see is this looks very nice. So we can increase the range from 1,000 up to about 7,000 in this Taylor microscale Reynolds number. Since it's the square root of the normal Reynolds number, that's why these numbers are all a little lower than I was showing at the beginning. How can you measure this? So the big question now is when you look at all these flows, there's, for example, these cryogenic flows or the superfluid helium flows, they have very, very, very small dissipation scales. The dissipation scales are of the order of a micron or smaller. And so it's very, very hard to measure. Even for our wind tunnel, it's a big problem because the injection scale is about 50 centimeter or 60 centimeters, but the dissipation scale is at 10 microns. Since we have to resolve this 10 microns, it's very hard to measure it with conventional technology. And one way to do this is to put a little sensing element, a hot wire, into the wind. This is in your typical car engine. There's a wind sensor, which also works most likely with a hot wire. And so this little hot wire, you let the wind go over it. The hot wire gets cooled. From the cooling, you keep the temperature constant. This would be a CTA, constant temperature anemometry. And from that, you can then measure the wind velocity in one direction. And so the question was, can this be done? And we were lucky. So there was Marcus Hultmark at Princeton who developed for their superflow a nanofabricated hot wire, which is shown here. So they are roughly, these are not actually wires. These are more like beams. So it's deeper than high. But the nice thing is that the length is about 4 times the Kolmogorov scale of our wind tunnel. So we should be pretty good to resolve this. So this is the probe, by the way. What you see here is just a electron microscopy picture of Scotch tape. So this is nothing special. This is just Scotch tape, okay? And so what you see here is the wire. And then with Detlef Lohse, we have actually just recently fabricated with a Dutch group, we have fabricated a real nanowire. So here's a platinum nanowire. Here you see the wire going across. And so these wires are very small. If you're interested, it's in this preprint, which is right now under review. And with this one, we can basically do the same thing now with a different second device, where you can also get very good results. We're just getting it. They break very easily, I should mention, but you can do very nice measurements now with this because these wires are really smaller and getting really to the Kolmogorov scale of the flow. So this is very, very promising, having 2 different devices. And so now let me talk about Eulerian statistics. So as I said before, we have this flow, and in this flow we have these structures here. And remember, we have the energy cascade, but it's really in space. It's not in time. So one way to look at this is to look at velocity fluctuations in one of these, in these pictures. And so what you ask yourself is, what is the velocity? One of the clever ways of analyzing this, just to look at velocity differences, then to look at the variance, to look at the higher moments of this. This can be very easily done with a hot wire like this in one direction, because you have the flow in the flow direction. You basically can use the time delay to get the spatial structure out of the flow, as long as the turbulence fluctuations are very slow compared to the mean flow of your structure. And so you can actually deduce this very nicely from measurements. There's a long history on this, going back to Taylor and Frontal basically in the 30s, and then later on there were a lot of measurements like this being carried out for years and years and years and years. And the question was, could we find a universal property in terms? Can we find a universal behavior? And the reason for that is coming from the Karman-Howard equation, where you can actually derive from fundamentals out of the Navier-Stokes equation this relationship, and where this is again the velocity difference. These are the higher order moments. This is the third order moment. Now, if you have a stationary flow, this guy falls away. If the viscosity is unimportant because you had extremely high Reynolds number, you get the famous 4/5 law of turbulence. Epsilon is just the energy injection rate that I put in, or it's just a dissipation rate, which it has to be equal to, because the energy, of course, is conserved. So what you put in at the large scales has to be dissipated at the small scales by friction. And so if you do that, then at the end you get this relationship, and then you can go back to Kolmogorov in 1941. And he basically said, from his analysis that he did on fracturing processes and so on, he realized, well, if you have these structure functions, it might be that they actually scale as Sn scales like n to the third. Nowadays, we know that this is not true. There's intermittency corrections, and I want to talk about this briefly here. So what you have is, you have this Kolmogorov 1941 work, which said that the structure function should scale like epsilon r to the n third. And then there was a lot of work. So in 62, this was corrected by assuming a log normal distribution, because everybody realized it can't be Gaussian. And then Mandelbrot, Srini, and Frisch, and Dubrel, and Shea, and so on, they really worked and put a lot of effort into this, also Charles Monimo. And they realized that most likely putting this, just assuming that there is no fractal structure behind this dissipative process, makes no sense. And so people came up with a multifractal process and were able to describe actually the behavior extremely well. And then in 1993, Benzi et al. Came along and they said, well, perhaps we should use this S3, that it should be exact, which should be the four, which should be, as I pointed out, which should be like this. If we take that one and we normalize all our structure functions by this, perhaps we can get a better idea of what the scaling in this universal turbulence might be. Okay, so let me continue. So what that means is it looks like this. So you have at small scales, you have the dissipation range, which goes like R squared. So if this is the second order structure function, or like Kolmogorov, in the immediate scales, it should go like R to the 2/3. And at the large scales, it should just be the RMS. And this R to the 2/3, if you go to Fourier space, is K to the minus 5/3. This is something you probably have heard many, many times. And so one is just Fourier space, the other is real space. And so what would you expect? Well, what you would expect is that if you have large enough R lambda, then you should have the injection scales here. Then you should go to this scaling where there's the scaling exponent. When you look at this local scaling exponent, which you can do with this log derivative, and then it should get constant, and then it should go into the large scale. So there should be this region where this just should be a flat line. And so what we did is we try to do this now in our wind tunnel where we can go to really high Reynolds number, the Reynolds numbers that you otherwise can only achieve in atmospheric flows. And so what we see, so this is a really low Reynolds number, so it's clearly it doesn't work. Then we went up to 413, that's better. 619, still better. Then we go to 931 and so on. And then suddenly we realized we can go up as much as we want, nothing happens anymore. It just seems to stop. You see, this is now 6,000, that's the highest we can go and the highest we trust still the data on. And so that means we do not achieve this because the distance goes up. So here it's again, right? So this is the low numbers, and then suddenly it seems to converge to this. You see here, even it's totally on top of each other. You see this? The curve is completely on top of each other, which means here, this is for 5,800 down to 2,300, right? All these three curves on top of each other, which means there's no hope that in our tunnel we ever see the situation that we get a flat line here. And the big question, why? Why would we see this? So what we found is there's a universe, seems to be a universal shape for our wind tunnel, but it doesn't agree with the normal K to the minus 5/3 scaling or R to the 2/3 scaling that you would expect. And so the question is, can we analyze this a little more? And I do this now. So what we did is we said, what is the value of psi at these different points along these lines? So we just take different points and plot them as a function of R lambda, which is the Taylor. So here's the Taylor microscale. This is this C measured at these different points, the local slope. And what you see is that with increasing Reynolds number, they all seem to saturate in the second order structure function. So that means there seems to be something universal popping up. It seems to converge, but it's not the Kolmogorov scaling that you would hope to see. Now you can do this also for the third order structure function or the fourth order structure function. You do the same little game, and what you find is they all saturate, but they don't come to what you would expect from the structure. So here's by the way, the third order is very nice. They all come together. Here they don't. And so what that means is for R lambda 2000, there seems to be not much happening in our tunnel anymore. We are pretty much done. We are in some kind of universal range, but it's not what you would have expected. And I will solve this in a moment, why this is the case. So what you have to realize is the following. So we have this grid. At this grid, we have a convective instability. At this convective instability, we get vortices. These vortices propagate downstream, interact normally with a triadic interaction. So there's three wave numbers that interact with each other. We get a turbulent flow far enough away from the grid, and this is what we investigate. So what that means is that while this turbulence is going down, it's actually decaying. Energy is being used up. It's not like we are feeding energy constantly in the flow. It's a wind tunnel, right? So we make energy once, it's decaying. So we're actually looking at decaying turbulence, and this was investigated by Yang, Pumier, and Zhu in 2018. And they asked themselves, what happens under different situations in decaying turbulence? How can we correct for the decay? And so what we find in our tunnel is that the length scale doesn't seem to change. Because our tunnel we attribute this to the finite size of the tunnel. and we don't see that the length scale in our flow changes. So this means we just lose some fluctuating velocity. And then we can put this in and assume with this power closure from Yang, Pumier, and Xu that they used, we can get a formula which looks like this. It looks a bit complicated. We don't have to understand it. But what's important here is there's only two factors that we can fiddle with. This is this amplitude AK and the second order structure function exponent that we would get for a non-decaying flow. So this is the second order structure function exponent C2F for a non-decaying flow. And then we can say, let's just fit to this and see how far we get. And so we have done that. And so what you can do, and so a student of Srini actually has done this, is so you take the so-called bachelor fit, which means you make a fit where you take the assumption that you know the small scales, you know the large scales, and in between you have an interpolation formula, which is called the Batchelor interpolation formula, which was done by George Batchelor. And then what you see is in the region where you actually want to fit, it doesn't work that well. But if you do the confined domains stuff from this is our measurement. So from, it looks different, but this is from Pumier. So we take the fit from Xu, Pumier, and Yang. And then what we do is we get a very good fit. I can zoom into this. And so here I did a zoom in. And so this is the Batchelor interpolation formula, which swings through this and makes artificially this plateau here. While this other formula very nicely fits exactly where we are interested in, namely the inertial range, but it doesn't fit very well at the small scales, and it fits better at the large scales. But this one can argue about, but it fits extremely well here. So let's look at this. Let's see which correlation length does the code actually give, so we can do this. The third order structure function works still quite well, but then it fails. So what we see is that the large scale, it seems that the large scale effect includes statistics throughout the entire range of scales because of this decay. And the flow is, of course, instationary, it's decaying, and so we have to use a different way. It's not allowed to use a Batchelor interpolation formula for our flow. We actually have to use something that's get closer, and this is what Yang, Pumier, and Xu have done. And let's see how far we get. So when we do this, what we find out is that the second order structure function, which is plotted here, as a function of Reynolds number, Taylor-Reynolds number, which we now get to 6,000. Remember, most experiments stop at about 1,000. We see that our decay model, so if we take the decay model, we see these nice blue points which are up here, or the red points over here. If we take a passive grid, which is just a grid made out of rods, then we also see that it goes straight. And then interestingly, if we take this ESS model where you normalize by the third order structure function and then calculate the effective exponent psi2, lies just dead on our measurements. So ESS, which also works down here, by the way, at very low Reynolds numbers where I can't measure anything because there's no inertial range, gives an extremely good agreement with what you get from this decaying turbulence under the assumption that it's decaying, and assuming that with this you get basically the exponent for turbulence that is not decaying but is constantly driven. So this is very nice. This is very nice confirmation of ESS, so it seems to make sense. And in addition, it shows you that indeed you find like in the simulations, for a flow that's constantly driven, which is not decaying, you find universal behavior where the second order structure function comes out to be 0.63 something. Here, 0.698 plus minus 0.011 for the second order structure function. So what that means is that the ESS gives the same value. It's all consistent with everything that was done before. And now we get out of our wind tunnel really a measure of this and also a confirmation of the numerical simulation. This all fits very well together. And also the intermittency correction that comes out of here, of course, was known because people try to understand this number of about 0.698. And so what you also see, so these are experiments from Cornell from a long time ago, also with an active grid. And you can see that they were far, far away by measuring a local slope. There is for those of you who know, at high wave numbers, there's a buildup of energy, which is called a bottleneck that can change your spectra a lot. And then you get also wrong numbers and you make a local fit and that just doesn't work. You just can't do it. You have to use, as a first order approximation, the things that Yang, Pumier, and Xu have done. And from that, you can actually get very, very nice results. So this is, I like this a lot because it makes me very confident the turbulence might actually be universal, but of course dependent on the flow. So you might find universal behavior at high Reynolds number, like in my wind tunnel, but it's not the Kolmogorov scaling that you get naively. You have to actually massage it a bit and understand your flow a little better. And then it turns out that the underlying theory might actually be okay. Okay, so let me go on to the next slide. I hope it works, yes. And so the question, so this is also something that Srini has written recently a paper about with Greg Bewley. And so when we look at the local slope and ask ourselves, what does it really look like? So these are the curves that I've shown you before. So this is the local slope of the second order structure function as a function of R, where R is normalized by the Kolmogorov length scale. And so what you see is they all collapse at the small scales as they should. And at the large scale, you just see there's different large scales in the flow. And so this is from 866 to 5,000. And let's just see how this curve really looks like. And what you can do is you can just say, well, it's almost straight here, right? So there seems to be a straight line. So let's subtract this straight line from the data. So we here zoomed in. So here's the straight line. Let's just subtract the zoom line. And what you find is you find oscillations. So when you look at this, you find some type of periodic oscillations, perhaps. And so what we have done now is we have taken this straight line, is this fit here, A times B log of R over eta. Once we have done this, then we get these oscillations, which you also see for the passive grid. This is the passive grid data is in this paper that Greg Bewley and Srini recently just submitted or had published. And so you see these oscillations. And then what that means is, well, do they exist for n equals 3? So that would be the third order structure function. No, they don't exist. But if we do the same thing for the fourth order structure function with a little bit of imagination, you can say they might be also there for the fourth order structure function. So it could be that the odd and even structure functions are different and you get these oscillations. Now the question, of course, is where do these oscillations come from? What could be the origin? And by the way, if you take the second order structure function, what you find is as a function of Reynolds number, the frequency of the oscillation seems to settle down to a value of about 0.3. So is this universal? I don't know. They seem to be there. Where do they come from? Well, here I summarize this again. So they're periodic. They seem to be only visible at even order statistics. They seem to be linked to the dissipation range, and they only seem to occur at all lambda greater than 2000. But there's a paper on this, and some of you might remember this. This is from the 90s by Didier Sornet, I guess. And he talks about discrete scale invariance in complex dimensions. And if you do this, then you get oscillations. And by the way, down here, 6.2, page 259 is turbulence. So it might have something to do with this, or it might not. At this point, we can't tell. But this might actually be an explanation of why you see this, because you have a discrete scale invariance instead of a continuous scale invariance. So it could be. And so let me just come to two more topics. So far, I have been talking about Eulerian dynamics. Eulerian means you take a picture of the flow and analyze this one picture of the flow and look at space. So it's really the velocity difference in space. It's not the velocity difference in time. This is very important. So when people talk about, this poem that you look at energy injected at large scales and it goes down to smaller and smaller scales and disappears into heat, that is really a spatial picture. It's not a Lagrangian picture. It's not really a time evolution of a fluid element that's being moved through the flow. It's just a picture of the statistics of this flow. And so what I can now do is I can look at the Lagrangian viewpoint, which means I'm following a fluid particle. This was pioneered by Yaglom and Opukov and Weizsäcker and others. They've pioneered this very early on because, of course, the fluid transport is very important for any geophysical phenomena where you think about transport of pollutants, for example. So you need to look at the Lagrangian evolution, also the mixing. You need to know the temporal behavior of the fluid and not only the spatial behavior. And so what I set out to when I left Cornell, the problem was we had a paper where we looked at Richardson dispersion. So Richardson dispersion says that if you take two particles in a flow and you look at the distance squared, so you just take the distance squared of these two particles somewhere in the inertial range, independent of the initial condition, it should separate by t cubed, t to the third power. If it would be diffusive, it would be T, of course, because it's length squared, goes like T. And if it's ballistic, it goes like T squared. At Cornell in our experiments, we could only find that there was a T squared behavior. We didn't see this T cubed behavior. And so when I went to Göttingen, I said, let's build this wind tunnel to measure Richardson dispersion. As I will show you, we are not there yet, but we are getting closer. And so the question is, can I take my wind tunnel at R lambda 6,000 and can I do particle tracking? Very difficult. You have a flow that moves with 5 meters per second. It's very slow. At the same time, you have to put in tracers that have a very low Stokes number, so they actually follow the flow in a way that you can trust it that it's really a tracer. And so I want to show you the data from Christian, which he has done. And so here I show you again. So these are these Lagrangian experiments where you have, of course, now temporal scales. You have a temporal correlation function. And what you need, of course, to do tracers, you need at least 10 measurements per Kolmogorov length scale, per Kolmogorov time scale. You need long tracks, so you need very fast cameras. You need about 20,000 pictures per second to follow these tracers. This is something I've been doing since 2000 for a long time. And so this is what was known. So here is some DNS from Taval from 2016, by the way. This is wrong, right, Taval? Is that wrong? I think you're not that old.
It's 2016.
It's 2016. I still haven't put in the new slide. I was told it's wrong, so sorry. But you're younger, Taval, okay? You're not that old. And so the question is, what is behind this cloud here, right? I mean, there's these measurements, there's these things up here, right, which is atmospheric data where they use kind of balloons. And then what's in the air? Is there something? Can we do it? And so we wanted to resolve this. And so here I just show you the first measurement. It can be done. So we use cellulose powder. Back here, you see where the cellulose is released. You see this little buff there? So watch it. Whoosh. And then we have a 300-watt laser, which illuminates our particles. We have stationary cameras mounted on the bottom, and then we measure acceleration. The nice thing about acceleration is you don't have to track the particles for long. You can measure the acceleration very easily, also locally. And just to show you that it can work, so here again is the video. Well, we are not that far yet. This is our measurement from Cornell, which is over here, and you can see the new measurements in Göttingen are pretty close. We have a lot of noise here because we don't have very good convergence yet, but we get all three components of acceleration and give us another year. And we have beautiful acceleration data down where this curve goes down to 10 to the minus 8 or 10 to the minus 10. Please also notice that this is, of course, plotted in terms of the variance. So this is normalized by the variance. So if this would be a Gaussian process, you should not measure something out at 50 standard deviations. There should be nothing at 50 standard deviations. So this shows you that this flow is extremely intermittent, but we know this since 2000 when we did the first measurements on this. Okay, so what that means is we can make a few points. And so if you look at the large scale, basically Lagrangian correlation time over tau eta, we now have already 3 points over here, but there needs lots to be done. The data has to be now done very thoroughly. But what that means is we now have a chance to actually do Lagrangian measurements and look at a completely different view of turbulence where there's actually no exact relationship so far, none, that comes from the Navier-Stokes equation. Everything you see in the literature is all done by scaling analysis. There's no real good exact result. So it would be nice also to get some mathematically better insight. But we're getting there, and we can contribute before they send me into retirement. I can hopefully finish this up before they take my tunnel away and sell it off as scrap metal. Okay, so what I've shown you so far is, and I still have a little time, right, Srini? Correct? Good. And so we have this active grid, we have this SF6, we need tons of it. It was a huge, huge time investment to get this going. Greg Bewley has done an amazing job in get this on the way. Holger Nobach has done an amazing job in building it. We have done, a huge amount. Jan Molacek, who was formerly at MIT, has spent a huge amount of time in doing particle tracking software. We are now getting to the point where this tunnel can be used also not only for Lagrange, for these hot wire measurements, but for completely independent measurements where we track particles. The advantage is we do not depend on Taylor frozen flow hypothesis, and we do not depend on a hot wire. We actually do real tracer part measurements. So we really measure the flow very directly. So this is very, very nice. And we hope, of course, that we can go up to our lambda 7000 in the near future. So let me go to the last part, which is very close to Daval's and Ellen's heart. The question now is, can we understand small scale intermittency in turbulence? And you might know that there is a price for the, if we could show that turbulence, that Navier-Stokes equation always has a solution and has no finite time singularities, then you can win $1 million. Now the question is there a cutoff in the does dissipation actually cut off the development of vortex stretching? Does it actually do that? And so here, for example, you see the vorticity, the PDF of the vorticity. You see you get these extremely long tails at very high Reynolds number. If you talk to Daval, who is now with Srini, so he's in New York, he can tell you more details about this. You need to do amazing numerical simulations with extremely high resolution to even get that far. Here you see a picture of the isosurfaces of vorticity and strain, and you can see that strain and vorticity are always in the same region. So you have something like a ballet tensor which gets stretched, so you get this blow up of vorticity. And so the strain raging actually is in the stretching direction here, right? So it gives you a stretching motion. And this has consequences for dispersion and flame tearing and so on and so on. And then you of course want to look at the key mechanism of this, and what you can do is you can write down the vorticity equation from the Navier-Stokes equation. What you find out is that you get this relationship here, and so what that means is strain x on vorticity, right? It amplifies vorticity, and then vorticity affects, of course, the strain itself because it couples back here, couples back, and so what you also notice is that this is strongly nonlinear, non-local. And so this is a huge theoretical challenge, and this is why this $1 million was not given yet to the mathematicians, because you cannot show that this does not lead to finite time singularities yet. And so there's this Clay Millennium Prize, which I talked about, which is this $1 million that you get. I think when they gave the prize, it was still a lot of money. If it's going to sit out there for much longer, inflation is going to eat it up. There's nothing left. Well, $1 million is still very nice to have, of course, nowadays. But can we actually understand this a little bit better? And so Daval and Elena set out to really catch this a little bit and to better understand this. And I don't have so much time, but one way to look at that is to use the Biot-Savart law that we know from electromagnetics. And so what you can then do is you can say, well, what is the velocity field that's made out of basically by this Biot-Savart relationship? And then you can take this integral in terms of, you can write this, the strain in terms of vorticity, which is written down here. And then you can write this as a part which is local and a part that's non-local, which basically goes to infinity. So you can separate the two in two parts. So one is the local strain near the vertical structures, and the other one is the non-local strain, which is far, far away, and you could even go to infinity. You basically a numerical domain. And so when you do this, to do that, Daval set out to do with P.K. Young to do an amazing simulation, which is over here. And so what they simulated up to 12,000 cubed. This, I always ask Daval how much energy this costs, and I'm sure it's much more expensive than my wind tunnel. And it's only 1,300 in terms of energy. So this type of turbulence research is not good for Mother Nature because there's a lot of heat generated by doing it. But nevertheless, it's absolutely important to do, and it's absolutely important to actually have this very high resolution that's down here, right? Here it's not so good, but here the resolution is very, very good, as you can see here. This is not so great, but here it's really, really good. And so if you do that, what you can do is you can look into the conjecture that I just had. Can you do this? So you can split the amplification in these two terms, as I said before. And what you realize is that this quantity is predominantly positive. So it's clearly showing you there's vorticity amplification in the flow. But what you can also find is, what one already knows is from this work by Konstantin in 1996, we know that there should be a bound for the non-local contribution. So if you put this all together and you ask yourself, well, what is this actually, the local term really doing? What is it really doing? So we know that this thing is bound. We know that now it really depends on this guy, right? If this guy would explode, then this guy would explode. But if this guy does not explode and might even be negative, that would say it's very unlikely that I have singularities in this Navier-Stokes equation. And so simulation. And so if you do that, what you find out is that if you look at these vortical structures and you look at larger and larger scales, you see that everything is positive here. Then you look at the local term and the non-local term. At the non-local, you see that the overall term has a little bit of negative terms. But if you look at the local term right around the vortical structures, you see they are highly negative. This you can do even more in this picture. And here again, you can see that they're highly negative. And so what that means is that here the local strain actually works against vortex stretching. It makes sure that this instability locally is damped out. So what we would argue is, and this is what Alain and or Daval and Alain argue in the paper and with me, is that indeed it looks like the Navier-Stokes equation has regular solutions. It's very unlikely that the Navier-Stokes equation actually has irregular solutions, because this damping would get stronger and stronger at any higher and higher Reynolds number. And so what this means, most likely that, well, it might actually be true that the Navier-Stokes equation is a good equation. So there's ongoing work on the alignment properties of vorticity with local and non-local strain. And with this, I would like to come to an end. I would like to say that the Navier-Stokes equation is most likely correct in describing fluid flows. Most likely there are no finite time singularities. I think we need to think about universality in a different way, because decaying turbulence might depend strongly on the way we produce the flow and how it's decaying. Remember our wind tunnel, I said the large length scale is not decaying. That's not necessarily the case. If I would not have boundary conditions, the length scale might actually be getting larger. So then I would have to do a different fit. And so it's flow dependent. We have access to these rare events at really high Reynolds number. That's much needed also experimentally. The acceleration measurements that we are doing will do just that. We will have access to very, very strong pressure gradients, and this way to very strong, very fast variations in the flow. So if the wind tunnel actually works the way I want it to work, then we will be able to actually make Lagrangian measurements. And then we are independent of these hot wires and of this hot wire technology, because any other technology will not work, like PID and so on, will not work. And so these Lagrangian experiments are really needed to give a completely different perspective on the problem. With this, I would like to thank my collaborators over the years, so Greg Bewley and Christian Küchle, who are really important for this, Haitao Xu, and many others, Alain Poumir and Daval, who have helped a lot in all this. And as you can see, I think turbulence is kicking, is still very much alive, and there's still lots of new things to be discovered. And finally, perhaps within the next 20 years, we might actually put a close, at least we should know that the Navier-Stokes equation is a good equation, and all the things engineers do are not wrong. So this would be very nice, but I think this will happen, and this makes me confident that we can do this. So thank you very much. I probably forgot to thank a lot of people, but thank you.
Yeah, thank you, Eberhard. So before I open it up for questions for everybody else, one thought is, if the length scale saturates, it's possible to solve the decay problem exactly. And I don't know if you have looked into it or not, but I can send you a little note on how it can be solved exactly and what to expect.
Sure. We're happy to do that.
I'll do that. I also want to say that
what we have to do, Srini, what we have to do for this, to use the formula from Yang, right? The only way we can
No, you can solve it exactly, because the length scale doesn't vary. So it's okay. I will leave it for now. Yeah. I also want to say that Greg Bewley was my graduate student. He went to work for Eberhard, and Daval, whom he mentioned a few times, is now at NYU. So in fact, we have had, through personnel, very intense collaboration with Eberhard, although we haven't written any papers. So I'm very pleased that you were here. You are here, at least virtually, and giving the talk. Now let's see if there are any questions. I'm not sure, Alexandra, how this is going to work. I don't see any questions in the chat box.
We have people can raise their hands. You can also feel to unmute yourself and chime in as you would do at the regular seminar. But I see Ken has his hand raised. Please go ahead.
Okay, very good. So I will let it go on its own, and you claim you do the moderating.
I just wanted to show this for Srini. So this is Greg, by the way, here.
This one is using water.
Just a second. So you see Greg walking down
the other one we call the crystal ball. It's a sphere made of plexiglass.
He built this experiment. He built this experiment.
In both of those experiments, we can study.
So just wanted to show you. Greg is. This is an old movie. Quite a few of these people. There's Sinhuber on there, who was a postdoc at Stanford with with Nicolette for a long time. He's also on this movie. So there's a little bit of a traditional movie here. There's even Michael Bourgois on this movie, by the way, Srini. So if you look exactly, the French were visiting us. We're doing experiments. He's also on this movie. I can highly recommend to make those movies because these are historical things which you can watch in 30, 40 years and say, oh, who's this? Who's that? Good. Okay, just kidding.
Right.
Okay.
Take your advice. Okay, all right.
It's also, by the way, a great way for experimentalists to show what they have done. Because later you can actually see what you really did, because later nobody will remember your machine, nobody. But if you make a movie, then later people can say, that's what they used. They used this Lagrange amplifier that gave very interesting results or something like that. I mean, it's very good. It's a very good thing to make movies.
So I think there is a question for you.
Yes, go ahead.
Hi, Eberhard. Thank you so much for your colloquium. I've read before that there's these anomalous exponents. So for the higher point function, let's say the 4-point or 5-point correlation function,
yes,
they have exponents that deviate from the scaling onsets.
Yeah, it's non-linear. Yep. Mm-hmm.
Can you measure that as well in your experiments?
Well, currently, because we might, if Srini gives me a formula that's analytic for the higher order moments, I can do it. Currently, the current technique can only allow us to do second order, so we can't do higher orders yet.
But they've been measured by a number of people, including us, from simulations and experiments. So we can tell you more or less what we know at this point, if you're interested specifically.
I mean, what you can do is you can do this ESS scaling, of course, that works, right? You can just go to higher order structure function with ESS. You saw that even our apparatus with ESS gives pretty nice results, right? So if you do ESS, you can, for the second order, it comes out to be the same, right? And the other orders look also pretty good. So that means we're not far off from all the other measurements that people do in large scale. So it's pretty solid that this functional form. Srini has done measurements at atmospheric turbulence at really high Reynolds numbers and so on. So I think we are converging that there's actually some kind of intermittency correction that we kind of can agree on. That doesn't mean that there's a theory for it. That just means that it agrees with some kind of multifractal models, which basically are fits to the data. It doesn't mean that we have really understood it from Navier-Stokes. That is still outstanding. And we still have to do simulations or experiments to really get them.
I see. And as a quick follow-up, sorry, you measure this 0.69 exponent, right? Where you
yes.
expected 2/3, and it seemed like it was about 3 sigma away. Is that some moderate evidence of a violation of the scaling relation, or is that you think that's
yeah, this means that it's not it's not exactly 5/3. That's what it means, right? So there's a deviation, right? Here you see it, right? And the evidence is pretty overwhelming, if you ask me, that this number is pretty good, right? And Christian is there, so he's the one who took the data. If he wants to say something, on my screen he's next to you. Christian, you want to add something? You have to put your microphone on, otherwise we can't hear you.
Thank you. Yeah, we can of course measure ESS exponents for the anomalous for higher orders, and then we get results that are very much that clearly point towards anomalous scaling and are also similar to what is measured in has been measured in the past. I mean, as you can see, ESS really also works when we have very low Reynolds numbers.
Right. So yeah, you can see that it works at R lambda 400, right? It's even here down here, right? I mean, this is really low Reynolds number, 120, right? So you get a very, very nice. Of course, in real turbulence, you can't get that because there is no inertial range scale, right? At 120, in your coffee cup, you don't have a fully developed inertial range. That's just what it is. But ESS still works in your coffee cup. Quite interesting, right? So, by the way, I should mention that this talk is. I got a lot of time savings because Christian has his defense next week. And so I could steal a few slides from him. So I'm very thankful to him for that, for some of his slides.
Nice. So on the note of the coffee cup, I was wondering, so what are the timescales for these experiments? How long does it take in your wind tunnel to actually, for the turbulences to form?
So Christian can tell you how long it really takes, but what we did is we did an extremely converged measurement.
Mm-hmm.
So we measured it for very, very. Christian, what is the typical time scale for one Reynolds number, one situation?
About a day.
Oh.
Between 4 hours and a day is one of these data points.
And the eddy turnover time is 1 second. So we have really converged statistics. What I forgot to mention is that the wind tunnel has the amazing property that you can change with the active grid. You can change the length scale, and with the fan speed you can change the velocity, the mean velocity. But with the kinematic viscosity, I can also change the Reynolds number because I can change the pressure.
Right.
And so what that means is you can make very different situations where you keep the length scale constant and the velocity scale, and you can change kinematic and so on and so on. So you can basically measure the same Reynolds number under completely different conditions.
Mm-hmm.
It makes the wind tunnel exceptional because this allows you to do that. I mean, I know that Srini is building, I think, a nitrogen tunnel, which will do similar things. And of course, the air tunnel at Princeton will do the same thing. So these are the three tunnels that, to my knowledge, have the probability that you can change the density. And by changing, that's why we call it variable density turbulence tunnel. And this way you can keep, by the way, the energy injection scales all the same. And you only change the kinematic viscosity, which is kind of cool, right? You only change mu. And everything else, the grid driving, everything is the same. The velocity is the same. And I should also mention the tunnel is very slow. The tunnel is only 5 meters per second. And this was intentionally built that way because we wanted to particle tracking experiments. And anything above 5 meters, I cannot afford. And so that's why we made a tunnel that is extremely slow. And that's also why we went to SF6 and high pressures. And we excluded air because with air, you can very easily get fires. And so air is very dangerous. Nitrogen is not, but air is very dangerous. And CO2 is a nasty, you don't want to have it, it's poisonous, you die of it and you suffocate. SF6 is pretty harmless. The only thing you should avoid is letting it out in the atmosphere because it's a really very bad greenhouse gas. 1 kilo SF6 corresponds to 1 ton, at least 1 ton of CO2. So that's why we are not allowed to lose anything. We have sniffers everywhere in the institute, in the experimental hall. And of course, accidents once in a while happen, but we haven't had any losses. So far, we can't measure how much we have lost. We cannot. So we have lost very little. And the gas is also very inert and is very stable. So we don't get much of. The problem is if you have electric discharges, you get hydrofluoric acid, sulfuric acid. But so far, the gas always has been extremely pure over the last 10 years. We always measure it to make sure that we're not getting HF in there, which would react away anyway with any metal surface, but you have to be a little careful.
And I know that you guys look also a lot into clouds, right? And into the weather making up there, the turbulent situation. Is any of these situations would be actually corresponding with respect to Reynolds numbers and all the parameters?
So we measured the turbulence on Zugspitze, which is Germany's highest mountain. And it turned out it was the most isotropic turbulence we have measured so far. It was better than actually the French washing machine or the wind tunnel and so on. So it was actually quite good in terms of a Lumley triangle. But our lambda was 3,600. And so the wind tunnel is now at 6,000. So the wind tunnel is more turbulent than what we measure in the boundary layer on the mountain.
Wow.
In the cloud. Of course, these are very harmless clouds. These are not very, this is usually in the summer, there's not much wind velocity and so on. In a real cloud, the velocities will be higher. And we know that from so what we do nowadays is we have a balloon with a helikite with wings where we fly up to 1.2 kilometers, up to 3 kilometers in the cloud, and then do holography measurements, PIV measurements, all the metrology measurements right in the cloud, stationary. So in the spring, this last spring, before Corona, I was with my group on 2 ships with 2 balloons for 6 weeks.
Wow.
near Barbados, all the way down to the equator, and we did cloud measurements there. So,
It's
but
fantastic.
it all ties very nicely into each other because, of course, clouds also have a strong impact through the convection, and you can very nicely see the convection rolls actually with the ship. You can even see the balloon going up and down because of the convection rolls on the ocean. And so basically this closes the fundamental turbulence that we do in the wind tunnel with the convection work that we do otherwise. So there's a very nice link now between the two, and the moist part is of course extremely important too. So and why do we do this, by the way? So one of the big problems is near to in the passat window. What are they called in English? It's about 11 degrees north and south of the equator. What you get is there's a region where these winds are, right? These trade winds exactly. In that region, there's the most important cloud for the Earth's climate. They are the clouds that determine how much the Earth is going to heat up or cool down in the future. And the models all show that the cloud cover in these regions will get less. If this should be the case, then the Earth will heat up much faster than we think. Because these clouds are very low clouds, they're very dense, they're cumulus clouds, they're being generated every day, new. So every evening you have a blue sky. Let's say every morning is a blue sky mostly. And then in the evening you get a crafty rain, and in the morning you have a blue sky. And so there's this normal daily cycle where you get these clouds. And the big question is, do they get less or do they get more? What is the situation, physics situation? We don't understand it yet. The models say they get less, but is it true? And by the way, if we have to change the climate, that's the place where we should do it. But this is far out. We had 4 ships there. There was an American ship, 2 German ships, and a French ship. And there was 4 or 5 airplanes that were flying around for 6 weeks. And so we have a lot of data now that we all have to analyze. Satellite observations, the whole thing. And it was a huge campaign. It was the other big German campaign. Germany had 2 campaigns. One was the ship that was frozen at the North Pole, and the other one was the Eureka campaign that Björn Stevens.
Alexandra, maybe we should let Eberhard go, right? It's 12 minutes past and 10 minutes past 12.
I'm fine. But if people want to leave, of course, people have left already. You can see.
I can see that we are also losing people.
We are down. So my group is still heavy. So Vladimir is
No, this is normally what we do that for 15-20 minutes after the talk. If you're okay with that, to rate if people have still some questions, they're welcome to ask.
Yes, those who have questions can surely ask.
Yes,
but
I can see.
Somebody has a question.
Many people have just
disappeared. They voted with their mouse, not with the feet. In a talk, they actually would vote.
We have here a question from our student Josh Tong. Josh, please go ahead.
Yeah, ask
sure. May I?
Yes, go ahead.
Oh, thank you. Thanks for that was a really cool talk. I was curious about your experiments and how you would do particle tracking actually with the laser. Do you have to orient it over different experiments to see, I don't know, in one dimension and then in a different way? How do you get in all?
So what we have to do is we have to work very hard to do forward scattering. Christian knows how difficult this is in the wind tunnel. It's really hard to do in the wind tunnel because you have to get the light in. You have to get 300 watts of light into the wind tunnel. Of course, in the wind tunnel, you have to deal with all the index of refraction problems with SF6, right? I mean, you don't have air, right? So all the optics is different and blah, blah, blah. And then as tracers, it turns out the best tracers are cellulose. So this was Freya Nordsieg, who Srini also knows, I think. So Freya came up with the idea of using cellulose, and it seems to work very well. And cellulose has the advantage that the lung digests it, so it's not something that's bad. It's the same powder that you put on TV to make your skin not shine. And so you can, if you want to buy 10 kilos of it, it costs nothing. If you buy 10 grams of it, it costs a fortune. And so this way we have finally found a way to make tracers. So Christian, what's the Stokes number? You had the Stokes number, Christian.
The most recent estimate is that for what we have measured is around 0.4, 0.5. But we can go lower, but that's the largest particles that we have. If we use smaller particles, which we're probably able to, we can get down to 0.1, I think.
And so it's really, and the imaging is really, it's 3 cameras, and the 3 cameras image 1 volume, and you look at forward scattering. So you get as much light out of the system as you can. If you look from below, you try to, you have to range yourself. Usually what we do is we shine light directly in the direction of the cameras. Of course, in the wind tunnel, it cannot be done. You have to look from the side, because otherwise the cameras would be sitting in the wind and you can't have that. And so we have them underneath and look from below.
Yeah, so you must need to they're not the laser is refracting through the cellulose. I can't remember if it's I'm not sure if it's see-through or not. Basically, how do you track them with your code?
Yeah, they're non-transparent. So the cellulose is non-transparent. So you get mostly probably me-scattering. So you have to be a little bit careful about the me-scattering lobes, right? I mean, you run into real scattering problems. You get me-scattering out of them. And by the way, you see the same thing, of course, on Zugspitze when you do cloud droplets. You can also see, actually, you can just see them. You just shine a laser in and you can see suddenly the sky gets bright and then it's dark again. You say, what magic is that? And then you remember Mr. Me, and then you say, aha, it's just me scattering. So there's a lot of, so Jan Molacek has gotten his code now so far that he can measure through the me scattering also the particle size of transparent objects, which is kind of nice. So he can also now measure particle size while doing particle tracking at 20,000 pictures per second, which you cannot do otherwise, because the problem is getting size is always very, very difficult. You know, you can get either fringes inside the droplets, or you can, that's pretty much it. You can do out of focus. That's what Jan does. But it's actually a huge effort to get size out of it. That's why no data has appeared yet from the Zugspitze, because if we don't know what the droplets are, we cannot say much about them. And so we needed the size, and this took years to program the codes and figure it.
Hey, Eberhard, I'm signing off now. So
Yes,
it's great seeing you, and I'm glad
but
you
you have a day ahead of you. See, for me, it's already evening. My wife is already not expecting me, so it's all fine. I can sit here for longer.
Okay, well, I have to give a seminar myself in another hour or so.
I know. I saw that. Yeah. So,
yeah, so I have to get my own things together. So I'll see you again. Thanks a lot.
Thank you very much for coming, Srini. Thank you.
Thanks, Alexandra. Yeah, okay. See you. Bye.
Well, I guess we should just stop, right, Alessandra?
Yeah, I stop. Let me just stop the record.